We are on 2A.4, composing with absolute value functions, all right? So we've been learning about absolute value functions, which is our V, right? F of x equals bars x. So here we have our example. Example 1, we're just going to kind of do a quick review of graphing a linear function, okay? So at this point in life, you should know how to graph a linear function, correct? What's the first thing you start with when you graph a linear function? The y-intercept. You start with the y-intercept. And in this problem, our y-intercept is -3. So we're going to go to -3, 0, -3. And then we go to our m, our slope, right? And our slope tells us our direction. So our m is 1/2. So we rise 1, run 2. Rise, run 2. Rise, run. And I'm going to repeat this pattern in reverse going down. So I'm going to fall and crawl. Fall and crawl. Fall and crawl. Fall and crawl. Agree? And pretend that that's the straightest line you've ever seen, because I've been trying really hard to make it straight. All right. At this point, we're going to talk about this function as it is. So right now, linear function is increasing from left to right. You have a clear x-intercept and a clear y-intercept. Yay, linear functions, correct? All right. In the part here, it says that it wants us to consider the absolute value function of a of x equals absolute value of x. Define the function h such that h of x equals a composed of p of x. What is an algebraic representation of h? Okay, so we're going to, remember, if it's written in this form, that means I'm taking p of x and I'm plugging it into a, correct? So therefore, h of x equals a composed of p of x, which means a composed of 1/2 x minus 3. Agree? Composition? Yay, nay? Do I need to zoom in for you? Can you see it? I can zoom in if you need me to zoom in. Uh-oh, wrong way. Try to make it zoom in for you. It lets me. Does anyone need me to zoom in? If not, okay, cool, because I couldn't find it. So we'll continue. All right, so once we have that, now we're going to write it as a y equals. So it says write y equals h of x as the same coordinate plane as y equals p of x, right? So that means go ahead and substitute it in, right? So this is telling me to take 1/2 x minus 3 and plug it into a of x. So what that ends up looking like is y equals h of x, which equals the absolute value of 1/2 x minus 3. Because I'm replacing x with the entire function. Okay, if you have a different color, this would be a good time to change to that different color. I need this bar to go away so I can change my different colors. There we go. So I'm going to change to a different color. I'm going to do purple. Now, what did we say for the past couple of days? What is the job of absolute value? Not normal, but positive. It's to take our output, whatever goes into the absolute value is going to come out positive. Does that make sense? So if I'm plugging in this function, whatever goes in is going to come out positive. So if I plug in here -8 into this equation, -8, right? So 1/2, what's half of -8? -4. What is -4 minus 3? -7. What is the absolute value of -7? 7. So my, what was a -7 now became a +7. And what's going to happen to all these points? They're going to do the same thing. All of my negative outputs are now going to become positive because it's going inside the absolute value. Does that make sense? So all of my negative outputs are now becoming positive outputs because they're going through the absolute value function. So where it's -6 at -6 is now -6, +6. Where it's -5 at -4 is now -4 at +5. Where it's -2, -4 is now -2, +4. Where we have 0, -3, we now have 0, +3. Where we had 2, -2, it's now 2, +2. 4, -1 is now 4, +1. So now all of my negatives have become positive. Is it going to change my positives? No, my positive outputs are going to stay the same. They're going to stay positive outputs. So this would be my new function. This would be my h of x. That would be me taking my linear function and plugging it into an absolute value function. So it says, for what values of x will h of x equal p of x? Well, the values of x are x when x is greater than or equal to 6. And the reason being is, where did I end up overlapping at? At when x is greater than or equal to 6. And why did they not change? Why did those values not change? Because they're what? They were already positive. And that's because they're already positive. So what did this model do to p of x? What happened? So when I plugged p of x into a, what did it do? So when I put a function inside an absolute value function, what should I expect to happen? What's the change? What's different? All my negative outputs became positive outputs, right? So for the values, so all the values x less than 6, x less than 6, negative values became what? Became positive. And that's why it still maintained that V shape, right? Because it's all positive. They're going to be all above the x-axis. Do we see that? All right, so I want to show you in Desmos how this works. So in Desmos, it's pretty cool. Remember, I usually don't like saying pretty cool with Desmos, but I am. So with Desmos, let's say we put in our p of x. We're going to type in p, absolute value of x, p parentheses x, equals, and p is 1/2 x minus 3. That's our p of x, right? Pretty cool. You can name functions in Desmos. All right. Then it said we had our absolute value function. Absolute value function. So a of x equals, you either can write ABS or you can press shift and your backward slash, which is above your enter button, to get the bar. Either way, doesn't matter. So you can type ABS or get that. Okay, so these are the two functions that we're composing together, right? We didn't graph our absolute value, so we can hide it. So before our transformation, is this what our window looked like? Our graph looked like? Pretty much, right? Then it said for us to compose together. So we were creating a new model, h of x, and h of x equals a composed of p of x. And it reads the composition notation. As long as you accurately label your functions, it will read your composition. Which I got, again, I'm not a fan, but I got to give its props, right? That's pretty cool. So as you can see, did we graph it correctly? Were we right? Yeah, we're geniuses. Oh my gosh. Okay, cool, right? I know you don't want to admit it, but it is. It's pretty cool. So we're going to do the second one, which is now on the second one, it says we're going to graph K of X, which K of X is P composed of A and X. So K of X equals P composed of A of X, which means that we're taking, what are we doing mathematically? We're taking the absolute value function and we're plugging it in for every X value. Okay, so the model of this would be y equals K of X equals 1/2 absolute value of X minus 3. And we're going to put it in Desmos, but we're going to use the composition notation in Desmos, the function notation. It's a funky looking A, but it's an A. Okay, so here I go to Desmos. So I'm going back to Desmos. All right, so we've already looked at H. Now we're going to create K. So we have K of X equals, and this time we have P of A of X. Oh, they need to put a 0. Okay, I'm going to hide the green one so we can focus on what took place. What happened this time when we plugged in absolute value into our linear function? At what point now are they the same?
-3.
Your same is defined by your X value. So at what X value are they the same?
0.
0. And then they continue to be same to the right, correct? So for our graph, we have, I'm going to draw it here. I'm going to switch my colors. So from here, they are the same. They go meow, 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 right? But here, they did what? What's the math word that took place on the left side? I'll help y'all. Starts with an R. Reflection. They reflected. So the values reflected over the y-axis. Do we see that? So the values reflected over the y-axis. So instead, we are now mimicking our, so whatever the positive does, that's what the negative x is doing. Whatever the positive x does, the negative x does. Whatever the positive x does, the negative x does. Which makes sense because if we just went over how do you graph linear functions? And if I look here, isn't this just me graphing a linear function at 0, -3 and following the slope of 1/2? Yeah, that's all that is. Okay, so for which values are they the same? Well, when x is greater than or equal to 0, they're the same. And that's because those are your positive x's, right? X is already positive. So when it goes into the absolute value, is anything going to change? Nope. All right, describing where is the relationship between the graph of P of X and K of X. The points were reflected, right? So your left points, your values, your x's, less than 0 are symmetrical. To the y-axis. And they're symmetrical because they're going to mimic their positive side. All right. So again, the difference here is that for our h of x, we plug the whole function into absolute value, right? And because we plug the whole function into absolute value, we changed its output. Does that make sense? For k of x, we only we took the absolute value of the x, not the whole function, not the output, but of just the x. So that means we changed our x's. And so therefore our negative x's now started doing whatever their positive counterparts were doing. Okay, how are we feeling? Do y'all think we can do the next one completely with Desmos? Yeah? All right, let's try it. So this is the next problem. We're going to do it all in Desmos, okay? Reason why it's a quadratic, so it's a little funkier to graph, but we're going to do it in Desmos, and Desmos will give us our key points to help us create the graph. So I'm going to go to my Desmos. I'm going to start a new graph, and my first function is called what? Was it q? Is it q of x? Q of x equals x squared plus 3x or minus 3x? Minus 2x minus 3. I knew there was a 3 in there somewhere. So here's my original unbothered quadratic. And the key points are -1, 0, 0, -3, 1, -4, and 3, 0. I don't know why this one didn't need to come up, but. And also 2, -3, but it just doesn't want to be friends. Okay, so here's my quadratic. Now we're going to be transforming it using the absolute value function. So we're going to put in a of x, which equals either ABS or the bars of x. Doesn't matter which one you put. We don't need to keep it visible. We just need the function locked in. So what it asks me is to first find our, what is it called? Our m of x. M of x is a composed of q of x. Okay, a composed of q of x, which means that when we write it, m of x equals a composed of q of x. Do we see that? So this means that I took the entire q of x and I plugged it into the absolute value function. And because I put the entire thing in the absolute value function, what did it do? What did it do? It made all of my output positive. Okay. So what was negative outputs now became positive outputs. Do we see that? Okay. The values that didn't change are the values to the left of -1. So values that are less than -1 stayed the same, and values that are greater x equal to 3 or more stayed the same. And the ones that changed, that reflected over the x-axis, are between -1 and 3. Do we see that? Yeah. Okay. So the next one is n of x. N of x, in our notes, says now we're going to do q composed of a of x. That means that we're replacing all of the x's. They're not just plain x's anymore. They're now absolute value of x. So wherever there's an x, I'm changing it to the absolute value of x. So this becomes q composed of a of x. I'm going to hide this so you can see the difference. What happened with q composed of a of x?
Like a little bit symmetric.
It's not a little bit, it is symmetrical. Is it symmetrical with the y-axis? Yes. What stayed the same were my positive x values, right? X greater than 0, greater than or equal to 0 stayed the same, and the values that are less than 0 changed. They reflected. They mimic their positive values. Do we see the difference? Okay, so this one was plugged into the absolute value function, and it went like that. This one, we plugged the absolute value in for x, and it came like this. Okay, so these are the two different impacts that an absolute value function can have when composing with it. It's either going to, if I'm putting the entire function in, it's going to take all of my negatives and turn them into positive. If I'm only putting the accent, changing it for my x, changing my x to absolute value, that means that my negative x's are going to now reflect, mirror my positive x's. Does that make sense? Yay, nay? Maybe so. Okay. So what, I'm not going to draw the picture because I did it there, but what we did put in, so what our m of x equaled a composed of q of x, which meant that for a, we were plugging in x squared minus 2x minus 3. If I was to graph this by itself, y would equal the absolute value of x squared minus 2x minus 3. That's what the m of x would be. Okay? And when we graph that, what did we notice? We noticed that our x values less than 3, but greater than -1. So between -1 and 3. Oh, it says when are they the same? I'm writing this in the wrong spot, guys. Let's go there. The y values became positive. I wrote it in the wrong spot. It goes in here. And I'm not erasing. Just follow the arrows. Okay. All right. So when x was less than or equal to -1 and x was greater than or equal to 3, the value stayed the same. That's where they're equal. And why did they stay the same? Because the outputs were already positive. Then when we did n of x is q composed of a of x, which came out to be n of x equals q composed of a of x, which meant that I'm taking all x values and turning them to the absolute value of x. So graphically, if I was to write it by itself, that would equal the absolute value of x squared minus 2 absolute value of x minus 3. And then you should be able to describe what we saw and what took place. Okay. Tomorrow we will pick up and you'll do your exit ticket because I'm sorry. Oh no, we ran out of time somehow. So you'll do your exit ticket, and all you're doing the exit ticket is you're coming up with your own f of x, but you're still using a of x, but you create your own f of x and graph the change. All right.